Welcome to another video of metric space. Today we will discuss the boundary points. First of all, the definition of boundary points. Boundary points. Till now in the metric space we have seen some definitions. First is the definition of metric space. After that, open sphere, closed sphere, then open set, closed set. After that we have seen the definition of interior of set. Now suppose this is metric space XD and this A is subset of metric space X, then we say that A interior means just these points interior to A. So these are the interior points, just except the boundary points, all the interior points is denoted by A interior. After that we have seen the limit points of A. Limit points of A means these interior points as well as the boundary points. Now we will see the boundary points. Boundary points means these points, these on these, suppose these points on this sphere are the boundary points. So the definition of boundary points is, let XD be a metric space, XD be a metric space and A is subset of X. A point suppose X, a point X belongs to X is said to be a boundary point of A, is said to be boundary point of A if that X is neither interior of A nor interior of X minus A. X is neither interior of A nor of X minus A, neither interior of A nor of X minus A. So this is set A and this is the set of this X minus A. If you subtract A from the whole metric space, then this is the set of X minus A. X minus A sometimes denoted as this by this notation X minus A. We can write this X minus A in this form again. So here this X minus A and this is A. So X is said to be boundary point of A. We know that the boundary points means these points. So we say that X is boundary point of A if that X is neither interior of A. So the X is not interior of A, not interior of X minus A. Interior of X minus A are these points. So these are the interior. So but these points, only these points are neither interior points of A nor interior points of X minus A. So X belongs to X is said to be boundary point whenever that X is neither interior of A nor interior of X minus A. Or we can write this definition in other words as X, this X belongs to X is said to be, X belongs to X is said to be boundary point of A, is said to be boundary point of A if every open sphere centered at that point, if every open sphere centered at X intersects both A and X minus A, both A and X minus A. If we draw the open sphere on the boundary point, then that open sphere must intersect A as well as X minus A. So intersection with A is again non-empty, intersection with X minus A is again non-empty. So X is said to be boundary point whenever any open sphere centered at that X, that open sphere intersects X as well as X minus A. Now the notation of the boundary point is T.Y.B.Sc. The set of all boundary points, the set of all boundary points of A is denoted by T.Y.B.Sc. This is the notation of boundary points of A. So here in this diagram we can clearly say that these are the boundary points, and suppose I will do another diagram. Suppose this is metric space XD, then suppose this set A, this is suppose set A, then these points on this boundary are boundary points. This is very clear that these are the boundary points, because if you draw the open sphere on centered at this any x, then that open sphere also contains some elements of A as well as some elements of x minus A. This is point A, sorry, this is set A and this is the set of x minus A. Then that open sphere intersects A as well as x minus A. Also these points, the points on this boundary are neither interior points of A nor the interior points of x minus A. So this is the definition of boundary points. Now we will take one example. Find the boundary points. Find the boundary points of, first example is, suppose A is equals to open 0 close 1, then the boundary points on the real line are, can clearly say that this 0 is boundary as well as 1 is also boundary. If we draw the open sphere at 0, then that open sphere is open interval on real line. Suppose this is 0, this is 1, then if we draw the open sphere at 0, then that open sphere is open interval. For any real number r greater than 0, we can draw the open sphere and that open sphere intersects this A as well as x minus A. X minus A means the elements from except these elements. So if you draw the open sphere at 0, then open sphere intersects this A as well as x minus A. Also for 0, if you draw the open sphere and that open sphere intersects A as well as x minus A. Therefore the boundary points, notation of boundary point is dab A is equals to 0, 1. These are the boundary points. Now if you take the another example, suppose the second example is A is equals to close interval AB, close interval AB, and again boundary points are A, B. Now if we have given the third example as, suppose A is equals to whole metric space R minus singleton 0, whole metric space R minus singleton 0, then the given metric space is whole real line except 0. If we subtract 0 from the whole real line R, then this is our set A. Now to find the dab A, we can clearly say that only 0 is the element for which if you draw the open sphere, then that open sphere intersects 0 as well as that number. So 0 is only boundary point of A. Now the next example is, and the most important example, which is the standard definition of boundary points. Next example is, let A be a subset of metric space XD and show that dab A, that is the boundary points of A, is equals to A closure minus A interior, A closure minus A interior, or this can be given as dab A is equals to A closure minus A interior. Both the notations of A minus B, that is A closure minus A interior, are same. So this is the standard definition. This is the standard definition of boundary points. Standard definition of boundary points. Boundary points of A means the set of elements such that the elements of A closure minus A interior. This is the standard definition of boundary point. So to prove this, we have given that A is subset of metric space and we have to show that dab A is equals to A closure minus A interior. To prove dab A is equals to A closure minus A interior, we will just prove dab A is subset of A closure minus A interior. Also A closure minus A interior is subset of dab A. Now here we have given that let A be a subset of metric space, subset of metric space. Our claim is dab A is equals to A closure minus A interior. That is, we have to show that dab A is contained in A closure minus A interior, and this A closure minus A interior is also subset of dab A. Now to prove these two relations, first of all we will prove this dab A is subset of A closure minus A interior. Let we know that how to show this such inequalities. We will take the arbitrary element of dab A and prove that element is also from A closure minus A interior. Let x belongs to dab A. Now as x belongs to dab A, we have to show that this x is again element of A closure minus A interior. Now to show this x belongs to A closure minus A interior, that is we have to show this x belongs to A closure, but x doesn't belongs to A interior. X belongs to A closure, but x doesn't belongs to A interior. Now as this x belongs to dab A, since this x belongs to dab A, x belongs to dab A means for all radius greater than 0, if we draw the open sphere centered at that x, then that open sphere intersects A, that is their intersection is non-empty. Also that open sphere intersects x minus A. Intersection with x minus A is again non-empty. If we draw the open sphere at the boundary point, then that open sphere intersects A as well as x minus A. Now here we have this S R of x intersection with A is non-empty, S R of x intersection with x minus A is also non-empty. As this S R of x intersection with A is non-empty, this will give us x is limit point of A, x is limit point of A, because by definition of limit point in S R of x intersection with A must be non-empty, that is their intersection must contain at least one element of A other than center. We can clearly see that by previous diagram, if we draw the open sphere at any boundary point, then that open sphere intersects A. Open sphere, if we subtract the center from the open sphere, then also these some elements of that open sphere intersects A. So here x is limit point of A. X is limit point of A means x belongs to A closure, because A closure means A union limit point of A. So x belongs to A closure. Also as we have this S R of x intersection with x minus A is non-empty. Also this S R of x intersection with x minus A is non-empty. S R of x intersection with x minus A is non-empty means this open sphere does not totally lies inside A. This implies this S R of x. If we draw this diagram here, suppose this is metric space XD, this set, suppose this is set A. Now if we take the boundary point, x is boundary point, and draw the open sphere, suppose I will take this, and if we take this as center and draw the open sphere, and suppose this is open sphere, then this open sphere intersects A as well as x minus A. Now clearly we can say that this x is limit point, but this open sphere also intersects this x minus A. Here is the intersection, this is the all elements are from intersection of that open sphere and x minus A. Now as this open sphere intersects x minus A, implies this open sphere does not totally contain in A. This open sphere lies outside of this A. So this x is not an interior. By definition of interior point, the definition of interior point says that x is said to be interior point if the open sphere centered at that x must lie totally inside this A. But this at this x, if you draw the open sphere, then that open sphere goes outside of this A. So this x is not an interior point of A. So this S R of x intersection with x minus A is non-empty, that is this S R of x contains, this S R of x contains some points of A complement. This S R of x contains some points of A complement, that is our S R of x does not totally contain in A, that is our x is not an interior point of A. This implies x is not an interior point of A, Thus x belongs to A closure, but x doesn't belongs to A interior. Thus this x belongs to A closure, but x doesn't belongs to A interior. This implies we can write x belongs to A closure but x doesn't belongs to A interior. This implies x belongs to A closure minus A interior. This implies gamma A is subset of A closure minus A interior. Suppose this is equation number 1. Now we will show this A closure minus A interior is also a subset of gamma A by taking any arbitrary element of A closure minus A interior, and we will prove that element is also element of this gamma A. Now we will take, let x belongs to A closure minus A interior. Now as this x belongs to A closure minus A interior, this implies that x belongs to A closure but x doesn't belongs to A interior, sorry, x belongs to A closure but x doesn't belongs to A interior. Now this will gives us the x belongs to A closure means there exists some radius greater than 0 such that open sphere SR of x intersection with A is non-empty. By definition of closure of set means A union A interior. This, as this x belongs to A closure, x is limit point. By definition of limit point, we can write SR of x intersection with A is non-empty, and this x is not an interior point, and this x is not an interior point of A. Here x belongs to A closure but x doesn't belongs to A interior means x belongs to A closure means x may be limit point. So there exists some radius greater than 0 such that SR of x intersection with A is non-empty. Also x doesn't belongs to A interior means x is not an interior point of A. Now we can write this x is not an interior point means, after just write it here, and x doesn't belongs to A interior implies there exists some radius greater than 0 such that SR of x is not totally lies inside A. That is, this SR of x contains some points of A complement. That is, this SR of x contains some points of A complement. SR of x contains some points of A complement. Now SR of x contains some points of A complement means SR of x intersection with x minus A, that is intersection with A complement is non-empty. That is, we can write SR of x intersection with x minus A is non-empty. Here SR of x intersection with A is non-empty, SR of x intersection with x minus A is also non-empty. So from these two equations we can write there, thus we have, thus this SR of x intersection with A is not equals to phi, and SR of x intersection with x minus A is again non-empty. This implies x is boundary point of A, that is x belongs to set of all boundary points. This is equation number. So we can write A closure minus A interior is subset of gamma A. This is equation number 2. Therefore from equation 1 and 2, from equations 1 and 2 we get gamma A is equals to A closure minus A interior. This is the solution of this example. In this example we have seen that gamma A is equals to A closure minus A interior. This is the important example, and this is standard definition of boundary points. To show gamma A is equals to A closure A minus A interior, we just prove gamma A is subset of A closure minus A interior, and A closure minus A interior is subset of gamma A. We know that how to prove such inequality. Here x belongs to gamma A, be any arbitrary element of gamma A, and also that element, if that element is the element of A closure minus A interior, then we will prove, we can write gamma A is subset of A closure minus A interior. To show, we just take this element from gamma A, and by definition of boundary points we know that if you draw the open sphere centered at x, then that open sphere intersects A as well as x minus A. So for if this x belongs to gamma A, so that open sphere intersects A as well as x minus A, that is their intersection is non-empty. Now SR of x intersection of A is non-empty means x is limit point of A, and also this open sphere intersects x minus A, that is that open sphere contains some elements of A complement means that open sphere does not totally contained in A. So, that element, that point x is not an interior point. So, that was the required thing, that is x belongs to A closure, but x does not belongs to A interior. So, hence we can write that A is subset of A closure minus A interior. Now, to prove the reverse inequality, we take the element of arbitrary element of A closure minus A interior. This x belongs to A closure minus A interior. Now, x belongs to A closure, but x does not belongs to A interior. So, this x belongs to A closure means for all there exists some radius greater than 0, such that SR of x intersection with A is non-empty. Now, SR of x intersection with A is non-empty, and also this x is not an element of A interior means if there exists some radius such that open sphere contains some points of A complement. Now, this open sphere contains some points of A complement means SR of x intersection with x minus A is also non-empty. So, SR of x intersection with A is non-empty, SR of x intersection with x minus A is non-empty. By definition of boundary point, this x is boundary point of A. So, from this equation 1 and 2 we can write that A is equals to A closure minus A interior. Hence, the proof of this solution of this example.